Hello, welcome to lecture 12. In this lecture, we will continue with the net force on a parcel when this is displaced adiabatically in a compressible fluid. So we had derived that the net force is given by approximately G multiplied by d rho by dz plus rho G by gamma RT. Using the ideal gas law, P equal to rho RT. So we do first of all differentiate with respect to z. So if you do the differentiation with respect to z, so we have uh, dp by dz equal to rt d rho by dz plus r rho dt by dz. As dp by dz is equal to minus rho g, so this is the hydrostatic balance. So density and temperature gradients are related by, so this is the hydrostatic balance, hence density and temperature relations temperature gradients are related by minus rho g rt d rho by dz plus r rho dt by dz. So pulling d rho by dz, I mean all the terms um, to one side and then dividing the whole equation by RT, we get d rho by dz plus rho g by RT plus rho by t plus rho by t dt by dz equal to 0. And hence the force can be represented as, I mean it can be expanded as force F equal to G minus rho G by RT minus rho by T dt by dz plus rho G by gamma RT times H. Again simplifying this further by using the relationships that we have already used and also rearranging terms. This is equal to minus gamma rho G plus rho G by gamma RT minus rho by T dt by dz. Now as gamma r by gamma minus 1, this term is Cp, hence we can rearrange the term to be the force to be something like this. or this is just a rearrangement that we are doing just to get it to a form that is interesting to us. It's nothing new that we are doing here, just rearranging. So this is the force, this is the form of the force that the parcel faces as it is being moved from one location to another, and this quantity within brackets gives us the rate of change of the temperature, the actual temperature plus the adiabatic lapse rate, and this whole quantity, which is minus g by t, g bracket g by rho, g by cp plus dt by dz is defined as the Brunt-Väisälä for this compressible fluid. So writing down, define n squared is equal to minus g by rho d rho by dz plus rho g by gamma RT. So this is the quantity that we define as the n squared. I mean, this is what we have already gotten previously without simplification, and this means this n squared can also be defined as g by t g by cp dt by dz. Here n is same as the Brunt. I mean, the variable is same. It's just that its representation is different for a compressible fluid. So this is the Brunt-Väisälä frequency. So the oscillation frequency is dependent on the deviation of the actual temperature gradient from the dry adiabatic lapse rate. So this is the actual temperature gradient and this is the dry adiabatic lapse rate. So the oscillation frequency of a parcel of fluid in this compressible medium is dependent on how much on top of the adiabatic lapse rate the temperature is varying. Now this calls for a comparison with the incompressible fluid. Now we had done everything in terms of actual temperature, and we have shown that the Brunt-Väisälä frequency can also be defined for a compressible medium, and for a stable state we see that the oscillation frequency is dependent on the temperature gradient plus the adiabatic lapse rate. So this gives us an opportunity for comparison, and hence let's discuss something called the potential temperature. So this is routinely used in the context of oceanography and meteorology. So the potential temperature is the temperature attained by a parcel of fluid if it were to be brought adiabatically to a reference value of reference pressure. Okay, so this definition, I'll write down the definition. So temperature attained by a parcel of fluid if it were brought adiabatically to a reference pressure. Okay, parcel of fluid is brought from somewhere to a reference pressure. This is ideally, or mostly this is the sea level pressure for geophysical phenomena that's happening. So the reference pressure is the sea level pressure. So we define this potential temperature. This is denoted by the symbol theta. P over P naught is T by theta. So this is a adiabatic process, and this is how the theta should be according to adiabatic relationship. Hence theta, so this implies theta is equal to T by P by P naught to the power minus gamma minus 1 by gamma. So this is the definition of the potential temperature. Now when we have potential temperature, we can define a corresponding potential density. So corresponding potential density is sigma theta rho P by P naught to the power minus 1 by gamma. So this is the corresponding potential density. So the symbol for potential density, I am representing it as rho theta. So in terms of theta and rho theta, the Brunt-Väisälä frequency squared, this n squared, can be represented as minus g by theta, g by sigma theta, d sigma theta by dz. This is equal to g by theta d theta by dz. So this is a relationship between the Brunt-Väisälä frequency and the potential temperature and potential density. So now recall what we had derived for an incompressible fluid. So for an incompressible fluid, we had derived g n square is equal to minus g by rho d rho by dz. For an incompressible fluid, we had derived this relationship. So you can see that there is a analogy to the first part, that is n squared equal to minus g by sigma theta d sigma theta by dz. So this shows that the potential density effectively includes the effect of compressibility. So this this allows us to, this kind of a formulation, that is representing it in terms of potential temperature and potential density, allows us to consider this compressible fluid as an incompressible medium. So loosely speaking, potential density includes the effect of compressibility also. So now, based on this, the conditions for stability are d sigma theta by dz less than 0, this is stable case, and d sigma theta by dz greater than 0 is the unstable case. You can think yourself why this is so, and this is exactly the same as what we discussed for the gradient of actual density in an incompressible medium. So now we are representing the same static stability condition for a compressible medium, but in terms of the potential density. because this the potential density allows us to treat the fluid as incompressible. Of course, the fluid has not become incompressible, but this is just a mechanism for us to treat the compressible fluid. So we can write a statement: stability of the parcel of fluid is determined by the gradient of the locally referenced potential density. Okay, this is what is the statement form of this mathematical expressions that we had written down. This is a statement: the stability of the parcel of fluid is determined by the gradient of the locally referenced potential density. The gradient we are calculating only in the vertical direction. Please, that is something for us to take note of. So again, a schematic. So generally, so just talking about potential temperature, as we have been talking about potential temperature and density. So generally, with height, the potential temperature has a variation, which is of course expected. As temperature varies, potential temperature should also vary. And generally, and these are very average graphs, so generally it has a profile which looks something like this. This is a very general average profile. It need not always be the case. So this is a typical temperature profile. So typical profile of theta with height when the bottom, that is the surface, is warmer. Okay, so this is in the lower atmosphere, of course. So this is somewhere that a place that we are interested in. In lower atmosphere is how this the potential temperature varies. As you can see, there are regions of both stability and instability. Now, having discussed these conditions for stability, what is stratification, buoyancy, and previously discussing the governing equation of fluid motion, this is imperative that we discuss some scales of motion. That is, what are the scales that we are interested in. I have already mentioned this in one of the first few classes, that we are interested in large scales of motion, that is, which are affected by the rotation of the earth, and stratification is an important component. So we have derived already the effects of stratification, and now and previously we had also derived the effects of rotation. Now it's a related topic, but it's not exactly following up on the stratification part. Hence, there is something that we'll touch upon, which is new to some of us. So scales of motion. You will see how the scaling and the subsequent derivation of some non-dimensional numbers. So this will lead to some non-dimensional number. So this might be new to some of us. A Reynolds number is something that I think most of us have heard about, but we'll get to some more non-dimensional numbers that can be generated, because there are various parameters at play here. There's a rotation, there's a stratification, and if you include the effects of viscosity, you can create various different numbers, also including inertia. So the scales of motion is important because it will help us defining some non-dimensional parameters, which I mean, and the non-dimensional equations are important for us to understand. I mean, those are the ones that can go into the numerical solver that you develop to solve the equations of or the motions in the atmosphere and the ocean. So a scale, I mean, I said scales of motion, but it's important for us to define what is scale. A scale means dimensional constant. Okay, please remember, this is dimensional and this is also constant. Of dimensions identical to that of the variable. Okay, so the scale of motion, that is, we'll consider various variables when we consider motion. For example, we can define a velocity, we can define the time scale, let's say, or we can define a length scale. So those are the variables. So a scale means a dimensional constant of dimensions identical to that variable and having a numeric value that is representative of that variable. This is important for us to understand. So numeric value which is representative of that variable. Okay, so this is a scale, and this is used generally to reference the magnitude of the variable. For example, let's say you want to understand the speed of a certain disturbance in air. One of the reference variables could be the speed of sound in air. So that is a scale in your case. So for example, you want to understand the velocities, or you are studying, let's say, the speed or the motion of a certain fluid within in a channel or a pipe flow. In that case, your dimensions of relevance, so this is a pipe flow or a channel flow, the dimensions of relevance are the diameter or the length scales of the pipe. So this is the diameter. So this is where your system is confined to. So you can certainly select any other length scale. For example, you can select the radius of the earth to be a scale of length, but that will not satisfy this criteria, that this is representative of that variable. So radius of earth, multiple thousand kilometers, 6,000, more than 6,000 kilometers, will not be useful for us in this case of a pipe when there is a pipe of diameter, let's say half a meter. So that is not a representative variable. So we have to be careful while choosing the representative scale. So on that note, we will see what are the representative scales of atmosphere and ocean. So for different purposes, the scales that you choose will vary. For example, if you're looking at motion on earth, then you will be choosing the radius of the earth as the reference length scale. If you're choosing flows, if you're looking at flows in your lab, in your home, you will be choosing the diameter of the pipe as the reference scale. So that's the reason why I'm saying that scale is variable. It's not a constant. It's not constant for everything that are happening around us. So let's discuss some representative scales. So we'll write down first some variables. The corresponding scale typical oceanic values, typical atmospheric values. And I'm emphasizing the word typical here. Typical oceanic values, typical atmospheric values. There might be some deviations from these values also. So variables x and y that we routinely use for measuring the distances along the two axes. So representative scale, the variable that represents that that scale is capital L, and for ocean this is of the order of magnitude of 1 to 10 kilometers. So representative scales for motion. Okay, so this is the representative scale of order of 1 to 10 kilometers that we'll be interested in. And then for atmosphere, the similar length scales are of order of 100 kilometer. The variable z, that is the vertical coordinate, has a representative scale which is denoted by h, and the order of magnitude of the vertical extent of variation of a certain quantity, certain motion, is order 100 meters in the ocean and order 1 kilometer in the atmosphere. So these are representative variations of a certain variable in the ocean and atmosphere. So these are very averaged out, very typical, typical values, whereas these are not necessarily values that you always find, but these are the values that we often find. So what does order 1 to 100 kilometer, 1 to 10 kilometer mean is that typical motions might have these scales. That is why what I'm meaning by saying that these are the representative values. Okay, so these are the length scales that a certain process might have in the ocean. So in the x and y direction, you can see that this is much larger. This is much larger than a meter, whereas this the vertical length scale is approximately a few tens to hundreds of meters. Okay, so there is a scale difference. That is what we are getting at, and this will be helpful for us to define some non-dimensional numbers. The variable t, that is time, has a representative scale which is capital T, and for ocean and atmosphere, typical processes take a few hours to a day to vary, and for atmosphere this is similar. A typical process takes approximately an hour or a day to change or die down or come back to its initial position, quality. So once we have this, so we can define, once we have the coordinates and the time, we can define u and v. U and v are the velocities in the x and y directions, and a representative scale is capital U, and typical values in the ocean are order 0.1 to 1 meters per second. These are again representative values, and for atmosphere this is order 10 meters per second. So I'm just deviating from my column here. It's better to draw a line. Okay, so typical ocean processes happen within this range of 0.1 to 1 meters per second, whereas atmospheric processes happen in the range of 10 meters per second. These are again representative values. If there is a cyclone, if there is a strong ocean eddy, there will be it will have much higher velocities. And W is the vertical velocity. This has a corresponding scale variable which is capital W, and this is order of 0.1 centimeters per second. Whereas for atmosphere this is 0.1 meters per second. Please note this difference in units. So this is much lesser than the typical velocities in the horizontal directions, and this is what we'll also use later on. And again, similarly in the atmosphere also, the typical variation, typical velocities in the vertical direction is much lesser than the horizontal velocities.